you want to read what's on screen, during the demo especially, closer is better. So up to you. I promise I won't be smashing any pumpkins on the front row. So my talk is about training AI and your own data. The agenda for today I have is first to persuade you that there's no AI, only math, and that it's all in the process. So as a software architect and person interested in algorithms, I think this whole, labeling that we've been doing on things and giving them a nice marketable name may have made them a little less accessible to us who actually want to work with them. So there will be a little myth dispelling, but not too much. I'm going to focus on AI with your own data, maybe on your own laptop too, so that you can get started or see how at least I implemented what I was going to implement. The first thing to ask is, well, what are you going to implement? What do you want to do? Well, RAG, as we will talk about, is interested in solving this problem. A user asks a question, and then the system, in some magic way, using my own data, meaning it knows my stuff, not just general stuff in the world, using my language, meaning speaking in English and not in binary code, because I don't speak binary, I interpret it, responds like an expert, meaning I wanted to give me an answer that I on my own didn't have or know. I wanted to know to extend my ability. Otherwise, why am I asking it a question, right? And it should be somewhat intelligent. It should infer and understand me in a little more flexible way. I don't want to have to program it for everything I do. I want it to kind of get the gist and kind of roll with the punches. Meaning it should be tolerant of humans being imperfect. So in general, this is what the process is. There's user Bob, asks the question, where did I put my trousers? And the application at some point wants to return an intelligent answer saying, you are wearing them on your head. And this seems awfully silly, but Google can't do that. If you search in Google, it won't do that right now. And it doesn't do it because this is very specific knowledge that it wasn't trained on. The position of the trousers right now is different than where it was in the morning or last night. So that's the problem with training on any size data set, as intelligent as it may be, is that it's not your data or it's not the data set that will drive the right answer for right now. So that's the main motivation behind us wanting to take and augment information that my query is implying and augment the information beyond what the model or the backend system was actually trained on. So why not a search engine? Well, search engines are keyword-based. Keyword-based means that they are taking your sentences, your text, let's say, and they're breaking it up into words, and then they're trying to do things like stemming or synonym and map those words so that horse and horses is the same, and radius, radii, and radix is kind of the same, and moose and meese is the same, or whatever they come up with. But what they're doing is they're taking a word, trying to find some equivalence. That's the extent to which they are tolerant of you. So if I say, I want a hamburger, they'll have synonym for hamburger, and maybe synonym for want, like desire or stuff like that. But if you just say a hamburger would hit the spot, the whole "you would hit the spot" will give you all kinds of other things like "spot the dog" or other things, because hamburger is just a little piece of the sentence. So text search engines, as great as they are, and I love Lucene, and I love Solr, and I love Elastic, they're not quite cut up for this task. Plus, they suffer from the same issue, which is they need to be fed very up-to-date information to answer your questions. So if we look at the matrix of what we want from the system, we can see that a user can ask a question, yes, and you can even feed it your data, because as new information comes, you can put it into the system and have it re-index, and it'll be there. But it's not really using my own language. It's not getting English language and English expression in a great way because of the limitation of synonym and stemming. And it doesn't respond like an expert, so it doesn't enrich things from the vast knowledge beyond just that data. And it doesn't sound too intelligent. At best, it has existing information. It'll kick it back to you. That's the most you can hope from it. So what is RAG? It's an acronym, Retrieval Augmented Generation. The R, retrieval, means that it's going to use your own data. The augmented essentially boils down to prompt augmentation, and we'll see that in the process. And the generation means that it gives you, from all the whatever it used, a generated response that is not a regurgitation of an existing item that was already there. That's about it. Are we good with that? Retrieval augmented generation. Very simple idea. Take the stuff you have, munge it somehow to information that could be an instruction to the AI, to the model, to generate an answer, and then wait for the AI, for the model, to generate an answer for you. So the process in more gory details looks like this. For folks in the back of the room not listening to my advice to come into the spray zone, we're still asking, where did I put my trousers? The next step, though, is to take that text and tokenize it, break it apart, and give it to a pre-trained model that knows how to take those tokens and give you back some mathy vector. And I say mathy because there's a lot of math behind building it, but at the end of the day, it's an array of numbers, is what it gives you back, or gives back to you. So after we tokenize that question, we give it to a subsystem that knows how to make it into a vector. Those vectors are called embeddings. Why aren't they called something else? Yeah, bad marketing. They're in some places treated and given to you as tensor objects, sometimes as plain arrays, and they're all called embeddings because those words all make total sense and everybody off the street can understand that they are all one of the same. Then you take that vector and you create a query into a system that knows how to take vectors and find similar vectors. This is part one of the RAG system, where the system is way more tolerant than a search engine. What effectively is happening here, a vector is a pointer in space. You know, it's like, it could be n-dimensional on a two-dimensional, you know, it's just an arrow. And the length of an arrow and the angle of the arrow have meaning. So the vector search knows how to find, en masse, you have 1 billion documents, it knows how to scour your own data and find the data by that digest of this little vector. And it does so efficiently and quickly. Have you played with AI, anyone? Yes, you type it in, and it's like, toot, 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 toot. Hold on, I'm typing. This is because there's a lot of processing happening behind the scenes. That portion of the show can happen really quickly, actually. And it can go on all of your company's documents, all of the knowledge base you accumulated on your own, all of the whatever you gave. If you index the text with those vectors, and we'll see how we index with embedding, then that portion of the show becomes trivial. So now, after your question got transformed into Mathy, and then that Mathy went to a specialized engine that knew how to find documents related to this, and the top ones, you know, are the most related to this, now you have a subset of all knowledge that relates to your question. With that subset of knowledge, I can then walk up to, oops, sorry, wrong button. With the results of my search on my data, I take those top results and I create a prompt for the engine, for the LLM engine, for the model that I'm going to use to generate the response. In my case, what I will do is I will take restaurant reviews, see the ones that match the query I originally had, like where's a good burger joint or something like that. And then with those top results, I'm going to turn around and say, okay, people already reviews those restaurants. These are relevant to my query. Can you tell me why and where I should go? Where and why I should go to that place? And then I hand that query, that prompt engineered query, using the reviews, tell me where I want to go. If you just say, should I go? It's like, oh, what do you want? But if I already use the knowledge base I entrusted, which is the restaurant reviews that I decided are relevant, then it can give me a much better result. So that's the prompt engineering portion of the show, where I take some of the matched records that are real, and I give it to it and say, hey, these are real things. These are my criteria for you to continue and generate a response. Please give me a response. And then the pre-trained model that knows how to take text and give you back human-like responses gives me a result. And that finally goes back to the human. Dear diary, this is the RAG process in gory detail. This is it, in English. We'll see it in Python, but this is it in English. Any questions so far? Yes, sir.
So if I'm understanding the process correctly, it seems like in steps 1 through 5 are replacing the search engine. Like the rest. So like yeah, you're asking it in human language, but wouldn't that kind of imply that then the search engines for getting matched records are kind of obsolete if this process 1 through 5 is actually better, taking like a natural question and giving you relevant results?
Yeah, so I'm going to repeat the question for the sake of recording. Did steps 1 through 5, in which I took the user's input, did some magic and retrieved records? Dude, that's what a search engine used to do. So if this is better, ditch the search engines altogether. Sure, that could be a view I would support. Is there still a place for search engines? Well, it turns out that the quality and the relevance and accuracy of the system has to do with the embedding you choose to choose, and the ability for you to affect those results is not as high. So if you've hyper-tuned Elastic and submitted a different query, did static boosting, dynamic boosting, different stemmers, custom parsers, there's still a lot that traditional search engines have a lot more instrumentations for, and they will yield different results. Different better, different worse, not a judge. But yeah, But thank you, good question. Great observation, yes.
Thank you. And to piggyback on what both of you said, also, if I'm not mistaken with this, you do not have the source. It will not tell you, I learned this information that I'm giving you as an answer from this specific document, unlike a search engine which could. So it's impossible to trace.
So I wanna calibrate something here. When I started talking about like your data and how does it know, all of that part is actually, it's stage 7 here. The final engineered prompt I give to the model to expand on and generate, that portion is the portion where if I just go to ChatGPT, it doesn't know about the trousers whereabouts right now. So when I say my data, I mean actually that first portion of the show, the search engine-y part, where I keep feeding it the pants location all day long, or new documents coming in, new Q&As coming from the interwebs, whatever it is. So that portion of remaining current has to do with the fact that instead of retraining the model, the text generation model, to say, ooh, you learned another thing, another thing, which is very expensive, I delegate that portion to the vector search, which does a decent job and keeps relevant. Okay? One more question and I'll push on. Yes, sir.
What type of storage would be ideal for large language models to index or work from?
So the question is, what type of storage would be ideal for LLMs? The LLMs themselves don't quite, quote unquote, use storage in the same way, because an LLM is a saved model. A saved model is a mesh of polynomials with coefficients. It is an internal binary representation that doesn't map to using traditional tables or documents or anything in the back end. It's just a blob for all intents and purposes that creates a graph that they search in real time. So no storage there. In terms of the vector search, every major vendor has something, and today I'm going to demonstrate Atlas MongoDB, which has a vector search index that you can apply to existing documents. But every major vendor has their own stuff, and if you're just doing in-memory in Python, you probably use Chroma because all the samples are written that way. But in small scale, doesn't matter. High scale, there's vendors out there. Blob storage will not be it because it's not a database, doesn't have an index, it's not efficient. You don't want to do scans, you want an index. An index makes search fast. Yeah. Okay, I'm going to push on and we'll have time for questions as much as you want later. So I said models do stuff. What do models do exactly? So they compute, in the embedding portion of the show, they compute a meaning or nearness by applying a vector similarity. There is no AI, only math. Vector similarity can be computed. It produces a number. That number is higher when the vectors are near each other, whatever near means, and they're lower when the vectors are farther away. So I am famished, and I'd like to eat, maybe closer than I am famished and polar bears melting ice. I don't know, just coming up with stuff. But you can see that vectors will be generated, and some of them are closer, some of them are further. And it's just math to do it. The second portion of the show is a little of a misnomer because we were observing ChatGPT, whatever other things are out there in the market. We were observing that you type in a question and it gives you an answer. That's already a dressed up feature. Underlying the whole thing, it's all actually chat completion. What's chat completion? You know how you type in Google like Nuri is and it comes up with a bunch of, oh my God, that's what it thinks about me? So those are all probable things that Google decided just by ranking, hey, but popularity, what's the most, you know, like lunch in Pasadena is best at, and then it comes up with restaurant names because lunch already magnetized to some restaurant database and they did it and they rank stacked them by popularity. It's as simple and dumb as that. The AI text generation relies on that fact. It says, well, of all the vectors we saw in all the world, what are other vectors of already parsed knowledge that it has that most closely matches the vector? And then it turns and say, oh, you told me a piece out of a larger conversation I already indexed. Of all those large conversations, let me cull out what the likely continuation of that thought is. So that is what's called completion. And underlying all of the models have that. Some of them dress it up with already chopping out the part that you said in order to make it appear as if it replied to you. But in fact, all it ever does is complete your thought. So prompts really are initial vectors on which those become the basis for completion, and completion is the model giving you more text that matches it. It's all it does, really. So how are models built? How do they gain that capability? Well, we tokenize the input, and the input could be text or images, right? Because the model doesn't actually know the difference between famished, hunger, and a burger. They just don't know any of this. They have tokens, and they've seen these words kind of together, near each other, far from each other, in one document or another that they indexed. Same thing with pixels. If you train it on images, it extracts pixels, the nearness of pixels to each other, meaning their coordinate, their color, their whatever. And it doesn't know a dog from a rabbit. But if you start with a vector that kind of looks like all of the images of rabbits, guess what? The rest of it is also going to be rabbit because it's closer in n-dimensional space, but closer. That's all it does. So you tokenize the input, text, images, it doesn't care, it just tokens. You create vectors. Well, tokens are just kind of a vocabulary that it built a big dictionary of all the elements it saw and assigns each other a number. So you encode those strings and you get some token sequence out of the string and then you create a vector from it. And then you have also the reverse, which is from a vector like that, you can track back and regenerate the text that originally it was. That's where the magic is, because if you have that ability, it means when I say, I am hungry, where's a burger? And it saw kind of the hungry and the burger and it put it into a vector that lost some information. If it can deflate it back like a burger in Pasadena, then, and it's close by, then it will give me a English-like sentence from all the inputs it learned. So models are built by doing these operations, building an encoder and a decoder, and that is training the model, seeing a lot of information come in, doing a lot of math to jiggy things so that vectors end up being near each other when the meaning is, when the origins are close, and then further when the origins are not. And then after that is done, all of the parameters and all of the math coefficients used in the formulas are saved in a binary format in a model. That's what models are. So it's an action of mutating all of those input vectors and remutating again and again and again until the output is satisfactory. training is extremely expensive. Like tens of millions, hundreds of millions of dollars. The more data you train on, the more expensive it is. Is it always exhaustive, loop within loop, and loop on a billion things? No, there's more mathy ways to reduce that sum, but yes, it is extremely, extremely CPU intensive, extremely data intensive, resource intensive, and that means that training a model from scratch is very expensive. Retraining a model, there's something called base models, and that's something you might want to look into. Retraining a model is less expensive, but still pretty expensive. So if you have a base model that you like, it generates good English in response to general things, and you want your data to be part of the model instead of having to search each time, and your data is relatively static, retraining a model is something you can do. You can add layers to the model so that it can answer more relevantly to your own data. That's not what we're doing today, because that still is fairly expensive, and I just have a poor laptop here. Iterative, expensive to compute, and some randomness, meaning that if I took the same computer, same input data, and try to train it again without saving anything from the past, I will get different results. Which is why, I wanted to say GPT-3 and GPT-4, but they're actually different in more ways. But this is why when you see point version upgrades of models, Microsoft, OpenAI are very careful to tell you, oh, you're using something else. So yeah, sure, you can, but test again, make sure it's safe and good for you, because retraining a model does not necessarily get improvements and certainly won't generate the same responses all the time. So capturing a model is kind of an art still. The good news is we don't have to train a models from scratch, and that's what RAG is all about. We can use a model that is kind of generic and general, that's good at English, and then feed it the information that is relevant and new and specific to us and get the result. So a little about vector comparison. I said whatever near means. So from a math perspective, if we have a vector, let's say the vector v here in green, and we have three other vectors, a, b, and c, you could ask yourself, well, which one is closest to a? Well, A and C are shorter, B is longer. From an angular perspective, from what direction they point, V and B are the closest. V like Victor and B like Victor. A and C are shorter, and there are ways to compare. The easiest one is Euclidean distance. It's the one we don't use, by the way. V to B will be measured just by the point of the arrow, the distance from the point of the arrow to the point of B. And V to A will be the point of the arrow to there. So you can just imagine drawing a line between them and saying, what's the length of the line? And from that perspective, A would be probably closest, with C being second and B being last. Then there's the cosine similarity. Cosine similarity measures angle only. Doesn't care about how long the thing is or where it's projected in space. It only measures like the theta between this vector v and this vector b. So as we said, b is probably closer cosine-wise. And then there's dot product. And dot product takes into consideration well, I have another slide that tells us kind of what the coloring of this or how to think about it. Euclidean is just strict distance. Cosine is the angle and the direction. And dot product takes into account the direction and the magnitude. So it kind of doesn't look at the angle so much, but looks at the direction and the magnitude. So those are the three the one I'm going to use today is cosine, and if you play at home and you use some model that you downloaded from Hugging Face, it's important to look at the model card and see what is the appropriate vector type it uses, because you'd want to use that for your embedding. If your embedding is using a model that was trained with cosine, guess what? Your vector search engine better support cosine similarity comparison. If you do it otherwise, you'll get not good results. So what does that vector search do at the end of the day? Bottom line, vector search takes those embedding vectors, the one we took from encoding our text into some vector, and it creates an index on top of them, and it enables you to search across millions and billions of items really quickly using one of those three strategies. How does it do it? Well, the implementation, it's a little more gory detail. For MongoDB at least, they're using what's called ANN, approximate near neighbor. Strictly speaking, if you just did math and pandas and stuff like that, KNN is good, K nearest neighbors, which is a more strict, rigorous way of doing things, but more costly. It uses something called a HNSW, a Hansu. I don't know how to pronounce that. Hierarchical Navigable Small World. I don't know how to pronounce that either. This specialized index stores items in kind of a Z order, which we're familiar with in geo indexes, but enables quick search through it by storing very coarse distances at the top, and then from every node being able to dig deeper and deeper into more granular node. So you can imagine if, say, a vector points just straight up, it goes to the straight up bucket, and then it goes, well, not exactly straight up, between straight up and 45 degrees and find those, and then between 45 and 15 and blah, blah, blah. So it kind of stores all of the vectors in a hierarchical tree, which allows quick retrieval to the layer where things matter, and then it's much faster. Comparing every vector against the vector query would be inefficient. I have 1 billion items, I have to do 1 billion scans each time? No. But if I take the log of, let's say you have 72 layers in that HNSW, then it's a fraction. You only do like 50 comparisons at most or something like that to get to an answer. So that's HNSW. It's an implementation of one of the two algorithms, and then given a vector as a query, it just gives you a ranked list of things that matched against it. Another difference from a search engine. In a search engine, if you say, yo, soy something, and it never indexed Spanish, and it has no word for soy, no document matching soy, it will return 0 to you. Because this index is just helping you traverse distances, it will always return something to you because there's stuff there. And if you hear about hallucinations, major cause of hallucinations, that underlying the whole thing, when we're doing vector search, we're like, yeah, what's the closest? We're not saying, hey, is it within a certain radius only? Now, you can tune parameters and say, hey, don't give me distances that are absolutely less than 0.5. It's usually normalized to a scale of 0 to 1 or something. You can do things like that, but then you get a problem where if the encoding, you may hide information you want back. It's not that cut and dry, and it's relative, meaning that some vectors will be really close in the n space that it indexed, and they will come back, and some are further, but still are close enough to what you wanted. They would represent the right answer, So if you limit it to say, oh, I want absolutely less than 0.2 of a distance, cosine similarity, you will shoot yourself in the foot. On the other hand, because of that limitation, you bring results that seem a little bonkers sometimes. This is just some vocab, but I think I've impressed on you enough word similarity to get the gist. Token, it's kind of our tokenization. We take elements and we assign them a number. So rather than saying I need to store each of the word, I just transform them into numbers, and then I have a dictionary of that number means this word. In all the math, I use the number. If I need that word back, I just look up in the dictionary and get the word. Easy. A tokenizer is a machine that knows how to do it. An embedder is a thing that knows how to take those tokens, those numbers, and produce a vector. A model knows how to encode the initial text into vectors, do the whole thing, look for whatever, and also knows how to decode back from a vector to original text. And it provides completions, not exact matches. And training is what we talked about. Questions on theory? Can I jump into Python? I'll take 2 questions-ish, go into Python, and at the end we can take more questions.
So back when you were showing the, the training process, and you implied there was a random element to it, and then you said that they all come with a warning. Remember, this was version X, and this is a different version. How do you decide which one is the most effective, or is just whichever appeared first, or?
So training can be supervised or unsupervised. Unsupervised attempt to essentially round-trip things, meaning that they take all of the randomness, try to arrange the space of all vectors that describe the whole thing, and then they rank them on their ability to reverse the process. Given X, did I get encoded, decoded X back? And supervised training, a human goes and say, oh, this looks good, oh, this looks good, and they take a piece of the information that it never trained on and gives it to it and says, ooh, did it match my expectation?
So whichever one is presented is arguably the best, or the best found so far.
I'm not sure I get to the bottom of the question here.
When you say a pre-trained model, it is a model, right? And
Yeah,
just you said
so a pre-trained model here is just the notion that instead of me, Nuri, creating a model of all English language and learn the internet and all of the scholars and all of that, I use somebody else's pre-trained model.
Okay.
So I don't have to do that work. Yeah. One more question, and sorry.
Hello. I have a question. So can you use a different tokenizer than the LLMs that you are using to decode?
I'm sorry, again?
Can you use a different tokenizer than the LLM you use for decode?
So can I use a different tokenizers than the LLMs use? In essence, no, yes. Typically, when you go and you look for libraries, there will be things that are concerned with the length of the text and where to break it, and they will be built in. And in terms of breaking up the initial items before it gets fed to the actual tokenizer, yes. But the tokenizer itself it's
Yeah, because like a lot of examples, they're like, oh, you don't use like llama as tokenizer, you use a thing called sentence tokenizer instead.
Right, so sentence tokenizer is the generic, and you're saying, hey, can I write my own sentence tokenizer? Kinda yes. They're going to throw away things like squiggly braces and commas and spaces because they don't feel like it, or not. And I think there is still somewhere where you want to maybe change it. But the underlying mechanism that then takes elements and assigns them numbers actually has meaning because it's part of the training. So for them to say, my vector is fixed, has 100 spots, let's say, for them to say that, you know, the number is going to occur in this position or of this, the token is going to get the number X means something to the model because it means something in terms of magnitude comparisons it's going to do later on. So that portion of the show is actually the training. Yeah. All right.
Thank you.
I'm going to show, thank you. I'm going to show some code and what are we on time?
We have about, we have some more time still.
Okay. It's Sunday. If you need to go home, go home. If not, I'll stay after. How's that? Okay? There's also a keynote. I don't want to. Yeah. Okay. So let's close this. So that's the last slide. You can contact me, see me on LinkedIn. Otherwise, you know, see me after or forget about me if you really didn't like this. So we will start with a repo, and that repo exists on GitHub. Git remote-v. So I call it the AI foodie buddy rag MongoDB. So it's AI, the word I don't like to use, but it's popular. Foodie buddy because I love food. It's a RAG system, and it uses MongoDB Atlas as its vector search. And I do it because it's easy, and it works. There's other options to do it. That's fine. I'm also using Google models right now here. So I have two options for the model for generation. One is using Gemma, which was released fairly recently, and it's a great model, and you can run it locally on your machine. And the other is using their API, which means I make a call to the cloud and say, hey, here's your prompt, give me a response, which is also a possibility, and it works much faster than my lame non-GPU laptop. So how do I do it all? Let's do a quick read of just the foodie buddy itself. There's a bunch of imports. Where from? Read the docs. The first thing I want to do is I want to define a few things, and these functions are just served to use my MongoDB stuff and use the models, so you don't have to read too hard what it does. This one is the one that once I got some documents, I want to create, once I got an embedding, I want to go and ask Mongo to do something for me. So that's like step 3 of RAG, right? And what it does is it goes against MongoDB. It creates a MQL, Mongo Query Language pipeline, which is just a set of instructions. The first of is, you know, create me a vector search. Given an embedding, a vector, right? I want to create a vector search. So, you know, I pass it an embedding of a query, and the query vector becomes embedded into this query. Ta-da, nothing difficult. Well, after it found some documents that match it, most matchy first, least matchy last, do I want all of them? Well, these are restaurant reviews, and if they're restaurant reviews, I suspect my query matched restaurant reviews from many restaurants. So do I count this was awesome the same as this was great? I don't know. Well, so what I decided to do here, subject to experiment, is to take out from the restaurant review the text itself of the review, the name of the reviewer, just in case I want to show it, and then the GMAP ID, those restaurant reviews had like locations, GMAP IDs. And then what I do is I group by those locations. So a location that got many reviews that match my query will be high, and one that got less reviews matching my query was low. Is this the best thing? I don't know. For my demo, yes. In reality, if you roll it in production, of course, it biases against restaurants that have more reviews. You'll need to deal with that. I don't. So once I grouped it and I found the restaurant with the most reviews that are very relevant to my query, I just pick the top one. Because at the end of the day, I want this to recommend me a restaurant and say, you should go there, and here's why. So the you should go there is this one restaurant I identify as ranking at the top according to my criteria. And the why is, well, take those reviews, engineer a prompt, give it to the LLM, Gemma or Gemini, and let's go. So this is the query portion. This is how do I transform stuff. The embedding portion, I use an embedder. The embedder, there are different algorithms to do embedding. And for the embedding portion, I picked the multi-QA mini LM L6 cosine V1. Remember, it says cosine here, which means that my vector search should be indexed with cosine similarity. So I'm doing that. But this whole file can be reduced to a sentence transformer whereby, to the person's query, whereby I take some text and I use the model to say, give me a vector. Every embedding model has a certain token length. You can look at the model card on Hugging Face or wherever you got your stuff, or you can measure it really cheaply by saying, hey, embed me one text. It doesn't matter which text. It gives you a fixed size vector. That fixed size vector is important to Atlas search because it wants to know how wide the vector is. It doesn't matter how many words you give it. It always encodes it into a fixed size vector. So I just keep it and cache that token count just because it's easier for me programmatically, but you can also hard code it if you know which model you're using. So this is roughly it. Once I decided which embedder I'm going to use, I load it. There's a sentence transformer that I use, and then with the transformer, there's a method called encode. You give it text, and it gives you a vector. Dear diary, an embedder, you give it text, gives you vector. That's all the learning you really need here. So I got me an embedder. And in order to perform a vector search, I need to take the user's query text, où est le hamburger? I need to detect the embedder and encode that into a vector. If I got nothing, well, we're in trouble. Otherwise, I can create myself a Mongo query, that pipeline I just showed you. So I got the pipeline. I like to save that intermediately just so that I can show people that there's stuff, and during debugging, why not? I have that. It might be something you want to log statistically if you have a lot of users for your system to tell what kind of queries they're running, because when they say, oh, it sucked, it didn't work, you can go and see what they exactly searched. And then I go to the Mongo reviews collection and search with that. That is steps 1 through 5. Go, vectorize an embedding, go to the vector search, come back, give me results. What does a document in Mongo look like? It looks like a restaurant review with an embedding. An embedding is just an array of numbers. But every document in there got encoded. And if I added another restaurant review, I would take the restaurant review from the user, I will go to the embedder, create an embedding to it, slap the field on there, and voila. That's that. So that's that portion. Let me start off by running everything below, so hopefully as I talk, we'll get also results. So, blinky blink. We have those definitions. We have a vector search. It does actually the vector search, gives me some documents back. Then I need to define how to package those reviews that I decided are most relevant into a prompt for the LLM, for Gemma or for Gemini or Vertex AI or whatever they name it this month. So I need to take the initial user prompt because that was their query, and I want to take the results and I want to format it into text that I will give the model to generate the final G of RAG to generate the response. So I do it very ceremoniously by doing a JSON dump because guess what? The tokenizer throws away braces or makes use of them. So it's kind of useful. LLMs actually like that delimitation. It gives them some clue. So potentially they were trained with those. I don't know. So the LLM, the prompt engineering is write a restaurant review. That's my magic prompt. And my mileage will vary once I change that too. Write a restaurant review based on the question and reviews provided below. And I give the LLM both the question original from the user and the reviews. So now it's a one-shot. That's a thing in LLMs. It's a one-shot prompt to the LLM. Could I do it some other way? Yeah, there is a way. There's conversational or chatbots, and they just retain context. So one-shot is a way to just say, this is it. Other systems say, hey, how about, prime a query, say, as an expert in restaurants, please write me a review, blah, blah, blah. That's prompt engineering. Yes, play with it. See what gives you the best. This is all I could do on a Friday afternoon. So that's that. That just formats a prompt. And then what do I need? I need an LLM predictor. A predictor is different than the embedder because it uses a different model. The model for embedding is for the vector search. The model for generating is a fully trained, the best I can, run on my machine or in the cloud thing. So I was playing a little with text Bison and text Unicorn, both of them available, and both of them performed okay. These are not chosen for being the most knowledgeable about restaurants. They're chosen for being most useful for me on a laptop to run and to be able to generate text, having been trained on the English language, but not on restaurants or world, politics. It's just very good at interaction and Q&A type things. So those were trained on Q&A type information. So they're really good at predicting things that sound like Q&A, which is what I want. So I'm choosing a predictor with one of those guys, and that's my LLM, so my LLM predictor. And I'm using the API here, which means it's going to make a call over the interweb, and it looks like I do have networks. That's great. Almost done. So here the whole show is orchestrator. I vector search the query. I get the top search result from the vector. Then I look back and get the one restaurant and find from a different collection, hey, which restaurant did they actually mean? Okay, if I can find it. Then I create the LLM prompt, and I take the LLM predictor, one of those bison or unicorn, and I feed it the engineered prompt, get a result, and I show it to the user. The user is us, so let's look at the result. I asked, this is the first stages, the user prompt. I generated the query, blah, blah, blah. It gave me some restaurant ID, create an LLM prompt. So it says, write a restaurant review based on the question and the reviews. That's the fixed template. The query was, find me the best spam musubi that locals go to and is a hidden gem. And this, again, is from the template. Continue to answer using these reviews. And here are reviews that matched already from the vector. Those are actual user reviews that came from Big Island or something. And then finally, it composed text. That's the generate part, and it gave me a response. That's it. Yay. Woo. I did choose a Hawaii restaurant reviewed because they had less than 1 million, and my free account only allows so much storage. But, you know, you can go wild and it will perform just as well because vector search is a specialized index. So we have officially 3 minutes. So I'll take questions until we're actually out of time, and then I'll volunteer to stay a little after, but let those who want to leave do so without judgment. Yeah.
Thank you once again for that presentation. If anyone has any questions, feel free to raise your hand and I'll bring the mic on over.
So do different vectors give different results?
Absolutely. So the question is, do different vectors get different results? Yeah. I mean, if I asked, where is the best musubi, and where can I find the best musubi, those will be slightly different vectors, right? And the vectors of already indexed results, there may be one that's a little closer just because of the word I used or the tone or something. So yeah, absolutely.
So if I wanted to cure cancer,
yeah,
which vector would I want to focus on to get to the best results?
I wouldn't necessarily characterize this action as finding, it is not a clustering operation in the same sense that medical research does. So I wouldn't try to go about curing cancer in a RAG way. I would try to go about it by training my model on all of the observed data that got collected. And then I would, quote unquote, ask a question, meaning I would generate a measure of goodness according to some ranking of that. So this is built on language and text. It's not made for that.
All right, do we have one more final question?
If I'm understanding correctly, vectors encode meaning from text, and that meaning would be subjective to the model or tokenizer which generated that vector. Is there any system or capability for interoperating between tokenizers or models to interpret those in a similar way?
So let's try to get a little more, yeah. So those vectors are the result of a trained model. Even the embedder is a trained model that indexed things, and it laid them out into the n space, 384 different dimensions on these vectors. They laid them out in this n space in a certain way to make close ones close and further ones further. The word meaning is human. They don't know nothing about meaning. Nothing. They do not understand. A duck, a bear, a carrot, all the same to them. Pasadena, all the same. It's a token, it's a number. That's it. It's this spatial view that we take on this n space that for us humans say, the things that are close have similar meaning. In fact, from a math perspective, the things that are close are close. That's it. So anything else we layer on top of it is us as humans trying to use our language and our intelligence to do this. But from a system perspective, it's no more intelligent. So now you ask, hey, should there be different tokenizer to make things different? Yeah, absolutely. Is there one that's better than the others? I don't know. Ask an AI guy. From my perspective, I'm a user of, I don't know what happened here. I'm a user of those pre-built models and pre-built libraries, and I played with a few. There's LangChain, which I didn't use directly. Definitely the classics, the ML classics and have Torch, those kind of libraries. They have some treatment that lets you do things at an elemental and do it yourself. I use higher level libraries that packages for me so I don't have to deal with it. And if it yields me good enough results, where would I tune next? Prompt engineering. Probably would get me more mileage. Yeah.
All right. I want to let you know this has been Training AI on Your Own Data by Nuri Halperin. If I could get a round of applause for our speaker.